Hello, good evening, good day, everybody, and welcome to the latest episode of Ask Abhijit. Today, we talk about science, astrophysics, cosmology, technology, AI, all that good stuff. I hope you're all doing very well. Let us see, as usual, first of all, who all is there on the live chat. I can see Om Bekerikar, Prabhav, Vishal Kumar Verma, Salimong, Salimong Sangtam from Nagaland. Hello. Tanjiro Uchiha, liberal mongrel by Abhijit Chavda, Vladimir Abhijit Chavda, Pamel Nandi, Shri Vatsan, Muhammad Ismail, Namaste, Space KGB agent, my nephew or niece, is it? Dheeraj Singh, Siddhartha Sarkar, Kirti Kant Shah, Komal Jyoti, Shri Ramachandra Namaha, Tejas Swapnil Mishra, hello. Tejas, hello. Chinky, Gaurav Sharma, Akash, Anonymous, Gaurav, Nachiket, Dheeraj Singh, Priyanka, Prabal, Tier Games, Chandrasekhar Theli, Gakuse G, Shrivats, Rudraksh, Kaul, Ralla, Avinash, Captain America, Anshul Sinari, Chirag Avasthi, Bharat Satya 20, Samarth Acharya, Maulana Hawasuddin Al Pitroda, Geopolitical Dubey, Shaswat Pandey, Gyad Nistan, Vijay Sagar, Dikonda, Tanjiro Uchiha, Ajit Singh, Vinay Kumar HS, My Vision, Atif Rawan, Rahul Sharma, Disha, Strangely Proton, McLovin, Komal, Niharika, Vella, Insan, King Jatin, and everybody else. I'm going to stop here. Otherwise, I'm going to do this forever. So, as you, I hope, know, I'm going to take questions from the comments that you have, the questions that you put in the comments over the past week or so. So, let us get going with that. And let's find where's the first question? Do we have question number one? Okay, this is by Amrit Singh. Amrit Singh is a high school student. Recently, I was studying Heisenberg's uncertainty principle, and I found that in Resnick and Halliday's book, it was given as delta x times delta p is greater than or equal to h cross, and the same is given in Irodov's book. But also in some books, it was given as delta x times delta p is greater than or equal to h cross by 2. Yes, so it would be nice if you could clarify this, right? So Resnick and Halliday is a wonderful book. I have it somewhere over here. I think it's this one here. This one. This is. I think it's the sixth edition. I don't know which edition is out right now. Must be the 28th edition or the 73rd edition. It just goes on every year. This one here is the sixth edition, if I'm not mistaken, and it's a great book. It's a great book if you are a high school student or a college student. Okay, but it's not the most rigorous book that you will find. So it won't tell you how to derive the Heisenberg's uncertainty principle, and it's going to give you a heuristic uh, view of the Heisenberg uncertainty principle, but not the exact accurate thing. So let's search on Google for the correct formula. One second. Let me put that on the screen so that you can also take a look at what I'm doing. Okay, let's go to Google. And I'm going to search for the uncertainty principle. Heisenberg uncertainty principle. All right, let's go to images and let me show you that this is the correct thing. This is how it is supposed to be. So uncertainty in position times uncertainty in momentum is greater than or equal to h upon 4 pi, which is h cross upon 2, where h cross is the reduced Planck constant. Okay, so that is the correct equation or formula for the Heisenberg uncertainty principle. Now, what you find is that's the deal. That's the fundamental thing. Now, Heisenberg's uncertainty principle is a fundamental concept in quantum mechanics. It asserts that there's a fundamental limit to the precision with which certain pairs of physical properties, such as known as complementary variables, such as position and momentum, or energy and time, these can be simultaneously known. So the Heisenberg uncertainty principle sets fundamental limits on the precision by at which we can measure various phenomena. So this principle highlights the intrinsic probabilistic nature of quantum mechanics, of quantum systems. And there's a breakdown of causality sometimes over there because it's a very probabilistic. There are random numbers, etc., involved in this. And this principle arises from the non-commuting nature of quantum operators. Okay, so addition, subtraction, etc., it doesn't entirely work. Uh, so to really understand how the principle is derived, you have to understand various concepts like complex numbers. You have to understand expectation values, quantum mechanical expectation values. You have to understand statistical concepts like variance and standard deviation. You have to understand what Hermitian operators are. You have to know the Cauchy-Schwarz inequality. You have to understand the position, momentum, commutation relation, and so on and so forth. Okay, so if you understand all this, then you can actually see how the principle was derived, and then you will see that the one that's given in Resnick and Halliday is not entirely correct, but the one that I just put on the screen just a while ago, this, where is it? This one here, this one, this is correct. Okay, and H cross is the reduced Planck constant. The reduced part. So H is the Planck constant, and its value is 6.62 times 10 raised to minus 34 joule seconds. And the reduced Planck constant is about 1 times 10 raised to minus 34 joule seconds. So there's not much of a difference there. So you can see that it's approximately correct. So that's why certain books give it this way and certain books give it that way. But like I showed, the one that I put on the screen just now, that is the correct equation for the Heisenberg uncertainty principle. All right. Let's take the next question. The next question is by Pratyush Rai. And the question is, can you shed some light on the Fermi paradox? And what does it really talk about? Okay, the Fermi paradox. The Fermi paradox is, where's everybody? That's the Fermi paradox. So we have gazillions of galaxies and bazillions of stars in the observable universe. Okay, and assuming each star has one planet, you have more than 10 raised to 21 or more than 10 raised to 22 planets that should exist in the observable universe. And even if life exists on one out of a billion of these planets, or out of a trillion of these planets, that's still 10 raised to what, 8 or 9 planets. That's one with 8 or 9 zeros after it. Those many planets where life should exist. And if intelligent life is 1 in a million, then there should still be 1,000 or 10,000 or so, or maybe 100,000 planets where you have intelligent life that exists. So if life is so abundant, etc., so on, so forth, then where is life? Where is the intelligent life out there in the universe? We have been looking at the night sky and staring at the night sky for centuries, and we have very powerful instruments today, telescopes and detectors and whatnot, which look at the universe in a variety of different wavelengths and frequencies. We look at the James Webb Space Telescope looks at the universe through the infrared part of the spectrum. We have the Chandra X-ray telescope, which looks at the world, the universe through X-rays, through X-ray eyes. You have Hubble that looks at the universe through mostly visible wavelengths, and so on and so forth. So we have been looking for so long. We have radio telescopes, we have everything, and we have not yet detected a single sign of life anywhere, of intelligent life, of intelligent communication, of some kind of message or signal that indicates that it was sent by an intelligent, intelligent, from an intelligence, technologically advanced intelligence. So that's the question, and that's the Fermi paradox. If the universe should be crawling with aliens all over the place, then where is everybody? Where are they? Why have we detected nothing? That's the Fermi paradox. And there's something called the Drake equation. The Drake equation, let's put that on the screen, right? 1 second, let me okay, let's go and try and search for the Drake equation. Okay, where's the Drake equation? I'll put that on the screen. So Drake equation, and let's put that on the screen. So I'll not go into the details of what this all means, but this tells you how many. It essentially tells you how many intelligent civilizations should exist in the galaxy right now, in our galaxy, the Milky Way galaxy. And yeah, so depending on what parameters you fit in there, you will get various numbers. And the question is, if this is there, and if there should be the so and so number of intelligent civilizations out there in the Milky Way, then why has nobody contacted us? Why is there no signal, no sign of them out there? That is the paradox. So that is the Fermi paradox. It was first, I believe, proposed, the question was first raised by Wolfgang Pauli, one of the great geniuses, one of the giants who is responsible for the for our understanding of the quantum world and much more. And yeah, so that's the Fermi paradox, and there are various solutions that have been proposed. That first, maybe intelligent life is way too intelligent for us to understand it. So imagine that you are a science student in a high school or college laboratory. You have a microscope and you're observing a petri dish or a slide full of, in which you have bacteria. So you are looking in there, and you can observe those bacteria going about their lives on that slide under the microscope, and those bacteria are completely unaware of the fact that they are being observed. They have no idea whatsoever that there is something called vision, and that there are beings with eyes who can visualize things in various wavelengths, who are observing us. They have no idea whatsoever. So maybe we are like those bacteria, and there are super intelligences out there that are currently observing us, and we have no idea at all. Because 96% of the universe is the dark sector, dark energy plus dark matter. And maybe there are dark scientists and dark civilizations out there, completely made up of dark matter or maybe dark energy as well. And they are undetectable to us, but they can detect us somehow because they're so advanced and they are observing us maybe, and we're not aware. So that's one possibility, that we are being observed when we are not aware of it. Secondly, another possibility is that maybe these aliens, for them we are like bacteria, so they may be aware of our existence, but they may not be interested in communicating with us. Because, I mean, do we try to communicate with bacteria? Do we try to communicate with caterpillars? We don't, right? Do we try to communicate with ants? We don't. Doesn't you know it doesn't interest us. So similarly, for them, maybe we are not interesting. We are like bugs in a zoo or something like that. So maybe that's another possibility. Another possibility is that maybe there are certain filters that civilizations have to go through. Filters. So for us to reach where we have reached, life had to emerge on the planet. We don't know how life emerged. Then from unicellular organisms, we had to evolve into multicellular organisms. Our ancestors, far away ancestors, deep ancestry, and they had to survive various cataclysms and extinction events on the planet, the great oxygenation catastrophe, and various extinction events. Then those multicellular organisms had to emerge out of the ocean and onto land, and they had to ward off various predators, blah blah blah, all that stuff. And then our ancestors, after they had to survive the Chicxulub impact event 66 million years ago, and then they had to become bipedal, walking on two legs, and develop big brains. And then we had to develop various technologies as human beings. But a variety of our close relatives, like the Neanderthals and Homo habilis, Homo erectus, Homo whatever else, they all passed out, they all died out, but we survived, Homo sapiens. And then we have been able to develop various technologies essentially in the last 120 years. Since 1900, we suddenly discovered something called the quantum world, and that's why we have all this technology today. We had to pass through all these stages, and today we are at the brink of, we have certain very dangerous weapons. We have nuclear weapons, a gazillion truckload of nuclear weapons. We have that. More than 10,000 nuclear warheads exist on the planet. Then we have human mediated climate change, which could significantly alter our climate and cause all kinds of problems for our future generations, and that could conceivably lead to the extinction of humanity. Even nuclear war could lead to the extinction of humanity. So there are all these filters, great filters they are called. And it is possible that every civilization has to go through these great filters, and eventually they all die out because of this. That's another possibility. And one more possibility is that we are the only intelligent civilization out there in the entire universe, which is a frightening possibility, but who knows? We don't know, right? So it's all speculation right now. So that essentially, all of that, what I just described, is the Fermi paradox, and that's what it is talking about. Where is everybody? Where is everybody? Why don't we see anyone? That's the question. All right. Okay, Tejas says, when will we actually start mining resources from other planets or asteroids effectively? Okay, where are we right now? What is the current situation when it comes to space exploration? So we have the International Space Station in orbit around the Earth. Yes, and it's a collaboration of a number of countries that has given rise to the International Space Station. So we generally have what, two or three human beings in orbit around the Earth at any given point in time. Whether it's two or three or four, I don't remember. Let's say it's three. We have three people in orbit around the Earth, and we have a handful of countries that have human space flight capabilities. The US is one, Russia is one. Russia uses that for commercial purposes. It ferries American and other astronauts to space typically through its Soyuz launch vehicles. So the Russians have that ability. The Americans have the ability. You have SpaceX, which is a private thing player as well. The Chinese have the ability. The Europeans also have the ability to launch humans into space, and that's about it. The European Space Agency. India, in a year or two, will start its own human space flight program. So we have one space station, one single two space stations. The Chinese have a smaller one, but it's also a space station. So kudos to China to have developed that. So you have the you have the International Space Station and the Chinese space station in orbit around the Earth right now. The Russians don't have one right now. They can build one if they want to, but right now that's not on high on their list of priorities. India will have one in a decade or so. By 2030, 2035, India may have a space station of some kind. So we currently are in a position to send humans to low Earth orbit. Okay, 200 kilometers above the surface, 300 kilometers above the surface, roughly, give or take. The US is planning to send human beings back to the moon in a couple of years. Maybe next year, maybe 2026, something like that. The Artemis missions and all that. So within this decade, we will have the return, most likely, of human beings on the moon. So humans will once again set foot on the moon, and eventually by the 2030s, you will have some kind of a space colony or some kind of outpost on the moon. That seems to be the plan. By the 2030s, Russia and China will also most likely want to be on the moon, have a presence on the moon, human presence on the moon. By 2040, India wants to have a human presence on the moon, at least have one landing on the moon. So that's where we are right now. We are at a very early, initial, rudimentary, elementary phase of space exploration. Right now, we don't even have a presence on our nearest, uh, neighbor, which is our own moon, our own satellite. We don't even have a presence there. And the next step is obviously either Venus or Mars. And Mars is much more enticing because it makes more sense, because it is more Earth-like, and it doesn't have a horrifyingly hot atmosphere, and so on. So that's where we are. So first step is moon. Then by the 2030s, 2040s, we start hopefully having a presence on Mars. Now the asteroid belt exists between the orbits of Mars and Jupiter. And that's way out there. And the asteroid belt is extremely empty, essentially. It's essentially empty space. There are millions of these fragments of rocks and of various sizes. Some are large, some are tiny, and so on. But that's spread out over a gigantic piece of real estate in the solar system, and it's mostly empty. Asteroids are millions of kilometers apart from each other. That's the average distance separation between any two randomly taken asteroids that are neighbors of each other. So it is right now very difficult for us to even reach the moon. Then we'll have to reach Mars, which is even more difficult. And then to reach an asteroid will take, I don't know, at least a couple of decades to just reach one asteroid. And then to deploy the kind of mining equipment and all that stuff out there and extract that and bring it back to Earth will, I don't know, the technology will take at least 50 years, 100 years. So the way things are, asteroid mining is extremely far away in the future. It's not going to happen anytime soon. I'm not saying it won't happen. Maybe in the 2100s, you will have large scale asteroid mining if we develop the technologies reasonably well, and we don't. We still survive. We don't come across one of the great filters of the Fermi paradox. So it's possible, but it's gonna be a long time before this happens. Before this becomes viable and feasible, and before it becomes commercially viable. So I would say 100 years, perhaps. I hope I'm wrong, but I would say 100 years at least. Okay, Vedant Kulkarni has a number of questions. Firstly, if the universe is infinite and uniformly filled with stars, why is the night sky dark? And this is the Olber's paradox. Okay, so this question, I don't know who Olber's was or whatever. I don't remember the history. I mean, I don't know. But the question is, so 100 years ago, 200 years ago, 500 years ago, it was believed that the universe is infinite. Okay, at least in the West, in Europe. I don't get into the cultural thing part of this thing, but it was believed that the universe was infinite. And if the universe is infinite, it's a steady state universe, it's not evolving, it's just the way it is sitting around, it's infinitely large, then it would mean that there are infinitely many stars out there. So if there's an infinite number of stars out there in the universe, and they're at different distances from here, then eventually all of that light will reach the planet Earth. Okay, and there won't be any redshift, because there's no movement of the stars away from us, or any blue shift because they're coming towards us. They're just stuck wherever they are, in the firmament, so to say. So if there's an infinite number of stars in an infinite universe, then should this night sky not be completely bright? Why is it dark? That's the paradox. Okay, logically, if there's infinite number of stars, then we should be blinded by the light, because all that light should eventually reach us, but it doesn't. The night sky is dark. There's just pinpoints of light. So that is the paradox, and the resolution is very clear, very simple, that the universe isn't infinite. We have we have an observable horizon, the observable universe, which is about 90 light years in diameter, 45 90 million billion light years in diameter, 45 billion light years in radius. That's how far we can see in the universe. And then also there's also the fact that the universe is expanding, and the expansion is accelerating, which causes a redshift, and that ensures that even that much of the light of the faraway stars is redshifted. It is stretched out, which makes much of it invisible, unless we have something like the James Webb Space Telescope that looks at the universe in the infrared wavelengths and so on. So that is the resolution to the Olber's paradox. First of all, the universe is not infinite. There's an finite observable universe, and the universe is expanding, and the expansion is accelerating. All of that taken together ensures that the paradox is resolved. So that's the answer to the Olber's paradox. Okay, next question is, how does the black hole information paradox challenge our understanding of black holes and the quantum mechanics? So the black hole information paradox is about it's when we come at the intersection of quantum mechanics and the general relativity, that's where we have the black hole information paradox. So what is it like? So quantum mechanics tells us that quantum information is conserved. Quantum information means what is the mass of an elementary particle, what is the charge and spin of an elementary particle, what's the angular momentum, and various quantum states and all that. If you have an atom, then what quantum state is the atom in? If it has just one electron, like the hydrogen atom, then uh, what state is the electron in? Is it in the ground state? Is it in the first excited state, second, third, fourth? If it's a multi-electron atom, what are the various states of the various electrons? All of this is called quantum information, quantum states. Then you have something like, if it's just a photon, then what's the polarization of the photon, and in what direction, in what plane is the electric field and the magnetic field, these two fields, in what plane are they oscillating, and so on. So all of this is called quantum information, and according to quantum mechanics, which is a very, very, very powerful and very well tested theory, very accurate theory that really works. From the perspective of quantum mechanics, quantum information should be conserved. Quantum information cannot disappear. It has to be conserved. Now when we talk about general relativity, then we have a situation, a black hole. Okay, so from the perspective of black hole thermodynamics, a black hole is described by only three properties: mass, charge, angular momentum. That's it. Nothing else. Mass, charge, angular momentum. If angular momentum is zero, then the black hole is not spinning, and it's a Schwarzschild black hole, in which case its various properties are given by mgc, and so on. So a black hole is defined by only these three properties: mass, charge, angular momentum. What about the quantum information? Let's say you have electrons falling into a black hole. Let's say the black hole has an accretion disk around it, and it's swallowing massive quantities of hydrogen gas and various other kinds of gases and dust and whatnot. It's absorbing, it's swallowing photons. What happens to all this quantum information once all this gets inside the black hole? what happens with the information? Because the black hole is described only by the mass, charge and angular momentum. And then Stephen Hawking showed that black holes actually radiate, they evaporate. Black holes have a temperature, and they evaporate through a process called Hawking radiation. And whatever comes out of the black hole, whatever radiation comes out of the black hole, is black body radiation, which is random, which is probabilistic, it's random. Okay, and it doesn't encode the information that fell inside, the quantum information that fell inside. So here you have a apparent breakdown of quantum mechanics. So there is a disconnect and discontinuity between general relativity and quantum mechanics, and that is the black hole information paradox. And that tells us that there's either a problem with quantum mechanics or with general relativity. So we either need to improve quantum mechanics, there's a flaw somewhere in there, and we need to fix that, or we need to fix some flaw in general relativity. And it looks like the flaw may perhaps lie in general relativity, or maybe both places. We know there's something called a singularity in general relativity. A singularity is what lies at the heart of a black hole, okay, deep inside, way past the event horizon, at the center of the black hole. And that's where the curvature of space-time becomes infinite, and matter density or energy density becomes infinite. And when you have an infinity in mathematics, it's a division by zero, which means your equations have broken down. You're dividing something by zero, which means there is a flaw in your theory. So clearly, general relativity, which is a brilliant theory, which is very, very well tested at the large scales, that theory breaks down at the ultra microscopic scale. So yeah, that theory will need some amendments, some improvements, but not the kind of improvements that break the overall theory. And maybe quantum mechanics needs to also be changed in some manner, modified, amended in some manner. There are problems, there are certain issues that are well known in quantum mechanics. I mean, for example, gravity doesnhave emerge out of quantum mechanics. There's no, you can only use, if you can use gravity in quantum mechanics, you can have gravitational potentials and all, but you have to use them, you have to use the Newtonian potential, or you have to use a classical potential. And even when it comes to time, in general relativity, you have space-time, the 4 dimensions of space-time, 3 dimensions of space, 1 dimension of time. In quantum mechanics, time is an external parameter, it's a classical parameter, it doesn't emerge intrinsically out of the theory, and so on. So that tells us that there's a lot that needs to be done when it comes to we ideally want to find a unified theory uh, that reconciles these two extremely successful theories, quantum mechanics and general relativity. So we want a theory of quantum gravity. What is a theory? Nobody knows right now. There's a lot of work that's been done on string theory, which kind of attempts to give us a quantum theory of gravity. But yeah, string theory has its own limitations, and we can talk about that later. So yeah, that's the deal with the black hole information theorem, black hole information paradox. Now the third question is, if time slows down near a massive object due to gravitational time dilation, how do we reconcile this with the idea of a singularity at the center of a black hole where time is said to stop? Okay, so the time dilation is it's something that you will find in the special theory of relativity. You don't even have to go to general relativity to see time dilation. Dilation effects are visible. You can see in special relativity itself, and it has nothing to do with the singularity, which may be which may exist at the center of a black hole. Time dilation effects and of course time dilation also exists in general relativity, which is the actual proper theory. So time dilation happens when you are going at extremely high velocities, or when you are in the presence of a very large mass, or any mass. So mass, in general relativity, the entire universe exists on a stage or in a stage, which is space-time, 4 dimensions, and space-time gets curved when there is the presence of matter in it. So matter curves space-time, and the curvature of space-time tells matter how to move. And this curvature of space-time is what we feel as the force of gravity, Newtonian gravity. We feel it like that, but it's actually the curvature of space-time in 4 dimensions, not 3 dimensions or 2 dimensions. Okay. So time dilation happens because of the curvature of space-time, and you can look at the equations if you're really interested. It's not because of a singularity. You can have a mass that doesn't have any singularity. Okay, if you have a mass m and let's say it's a spherical object, but the spherical object, its radius is greater than its Schwarzschild radius, then it's not a black hole and there's no singularity there, and you will still have time dilation. So you don't need to reconcile time dilation with singularities. Okay, a singularity is a whole different thing. It's an artifact that emerges out of the Einstein field equations, and clearly there is something that needs to be improved in these equations, and what it is we still don't know. So there you have it. Okay, it's the two things aren't correlated. Time dilation, if you do away with singularity, it doesn't mean that time dilation will go away. Time dilation exists because of mass, or because of well, inertial frames of reference. If you have non-inertial or even inertial frames of reference, well, to go into this in detail, you'll have to at least study special relativity, because time dilation emerges very nicely out of that. Okay, Swapnil says, how did the alignment between Saturn and Jupiter impact Neptune's orbit, causing the late heavy bombardment event? Okay, what is this late heavy bombardment? Good question. So, when the Apollo missions happened, when the Americans sent astronauts to the moon in the 60s and 70s, I think, when was the last mission? I think early 80s or late 70s, don't remember. You can look it up. So, let's say the decade of the 70s, late 60s and 70s, that's when the Apollo missions happened. You had human beings going to the moon, landing on the moon, and bringing back moon rocks, moon soil samples and stuff. And these samples were then examined and tested and analyzed. And what they discovered, the scientists, the geologists, is that many of the samples were samples of molten rock that had melted and then reformed. So, and it became clear that there were gigantic impacts of asteroids or meteorites, or whatever you want to call them, space rocks, on the moon, let's say about 4 billion years before today. So the Earth Moon system is about 4.5, I think, billion years old, roughly. Okay, I may be slightly wrong here and there. You can look it up. So these phenomena, these gigantic events, impact events, happened about roughly 4 billion years before today, and the evidence is found on the moon. But the moon is right next to the Earth. It's a satellite of the Earth, which means that this bombardment would have happened on the Earth as well. But the Earth's crust in the entire system is very dynamic. We have water, we have a rich and thick atmosphere, and we have plate tectonics and a lot of movement, and also any impact event, it will, after a few million years, maybe after 100-200 million years, disappear mostly. We have some impact craters that are more than 1 billion years old, which still exist, like the Free Fourth crater in South Africa, for example, more than 1 billion years old. But most craters disappear very rapidly because the Earth's surface is very dynamic. So we don't have evidence of this bombardment, which we call the late heavy bombardment on Earth, but we have found evidence of that on the moon. Now the question is, how did this happen? So there's been lots of simulation of the early solar system, and there's something called the Nice model. It's named after the city of Nice in France, and that's where this model was developed. So according to this model, which is a very plausible model, initially the 4 gas giant planets. Which are the 4 gas giants? Can you name the 4 gas giants? Well, let me tell you, it's Jupiter, Saturn, Uranus, and Neptune. These are the 4 gas giant planets in our solar system. So according to the Nice model, these 4 gas giants initially had formed much closer to the sun than they are right now. It was a reasonably compact stellar system or solar system. And obviously the rocky planets, Mercury, Venus, Earth, and Mars, were on the inside. But those are actually insignificant when you compare them to the masses of the 4 gas giants. So the 4 gas giants had formed much closer to the sun than they are right now. And then Jupiter and Saturn, these 2 planets, they came into they came into a state of resonance. So a resonance is when the orbit of one planet becomes an integer multiple of the orbital time period of another planet. So let's say Jupiter, its orbital time around the sun becomes exactly twice the orbital period of Saturn around the sun. So for each orbit Saturn makes around the sun, Jupiter makes two orbits. That sort of thing. That's called an orbital resonance. So Jupiter and Saturn entered into this state of orbital resonance or orbital resonance crossing, which means that there was a crossing of the resonance, and this caused an instability in the orbits of the other two gas giants, which were flung further away. And outside, on the outside part of the or of the protostellar disk of the early solar system, you had these bodies called planetesimals, which are like small dwarf planet like or protoplanet like small bodies which existed in a large cluster beyond the orbits of the larger planets. And as Neptune went outside and further away from the sun, it came into contact with these planetesimals and disrupted their orbits. And this disruption of their orbits caused the orbits to get elongated, develop high eccentricities, to be thrown out of the plane of the solar system. And also it caused a lot of disruption and churn in the solar system, and it caused what is believed to be the late heavy bombardment, which is all these bodies which were outside, they were flung inwards towards the sun, and they ended up impacting not just Earth and the moon, but maybe also the other uh, rocky planets within the inner solar system. So that essentially is the late heavy bombardment event. This is one model of how it could have happened. Okay. uh, it still needs to be seen whether it is correct, but it is I believe the most popular and most mainstream theory, the nice model of how this happened. So that's how the entire thing took place according to this model. There was an orbital resonance crossing between Jupiter and Saturn, which impacted the orbit of Neptune, which was flung further away from the sun, and it ended up disrupting the orbits of all these protoplanetary bodies and planetesimals and rocky objects in the outer solar system, which somehow got flung, many of which got somehow flung towards the inner solar system and ended up causing the late heavy bombardment, roughly 4 billion years before today, on the Earth and the Moon, and probably the other inner planets as well. Okay, Rohan BD says, when we see Jupiter through a regular telescope using the visible spectrum of radiation, what we can see with our eyes, that's a visible spectrum, it appears in a certain way. Yes, when we look at Jupiter through visible wavelengths, what we can perceive with our eyes, it looks like a certain thing, right? The bands and the great red spot and all that. When we look at Jupiter through the James Webb Space Telescope using infrared radiation, it appears different. It appears, yeah, the image looks different. And when we use the Chandra Space Telescope with X-ray radiation, it still looks different. It's a whole different image that we see of Jupiter. When What then is the true look of Jupiter, the true appearance, the true shape and form of Jupiter? Are all these just illusions? We can never know what the true picture is, and that's why our scriptures say the world is mo maya. Yeah, is a good question. Yes, all of these pictures that we see are the correct picture, and the true picture is the completely composite picture, the superposition of all these pictures. So our eyes, they can perceive only a certain range of frequencies or wavelengths, okay, of infrared radiation. Infrared radiation is photons. Photons come in a number of frequencies or wavelengths. Frequencies and wavelengths are two sides of the same coin. uh, so photons come in various frequencies or various wavelengths, and we can perceive through our eyes a certain range of frequencies, which is visible light. VIBGYOR, that the rainbow. And we also have infrared radiation, which is infrared photons. We have ultraviolet photons, which are more energetic. Infrared photons have longer wavelengths, um, and smaller frequencies. Yeah, no, sorry. Infrared radiation has longer wavelengths. Ultraviolet radiation has shorter wavelengths and higher frequencies, which are more energetic photons. And then you have X-rays and you have gamma rays and ultra high energy gamma rays and whatnot. Okay, that's all the various frequencies of photons. And then we have long wave radio waves, and it goes in the opposite end of the spectrum as well. But we can only perceive a certain range of the entire spectrum of electromagnetic radiation, which is photons. So what we see is one part of the true image. And what Hubble and all these visible light telescopes see is one small portion of the true image. Then you can use Chandra, X-ray wavelengths, and you see a whole different image. That's also the true image, the true picture. But it's a small part of the true picture. So what we see through visible wavelengths is a small part of the true picture. What you see through X-ray wavelengths is a different small part of the true picture. When you use uh, when we use infrared radiation, like the James Webb Space Telescope does, we see a whole different picture, which also is the correct picture. So all of these pictures taken together form the true picture, and we see only through our eyes. We only see a small part of it. So the world is much more than what we can perceive. And then we have not even spoken about the gravitational wavelengths. I mean, gravitational waves also exist, and we are just beginning to take baby steps in detecting gravitational waves. And right now we are in a position to only detect gravitational tsunamis, not waves, tsunamis, waves with gigantic amplitudes. So such gravitational waves are only those that are created by the mergers and collisions of black holes, two black holes, or a black hole and a neutron star, or two neutron stars. That sort of cataclysmic gravitational event throws up a gigantic gravitational wave tsunami, and that's what we can detect right now. But what I would like to have happen is to develop the technology that would allow us to detect gravitational ripples in space-time. That's when the real universe emerges. So we have all these wavelengths of visible light, and we have not even spoken about gravitational waves. So all of that taken together, and maybe some other things also that we may not be aware of, all of that taken together is the true picture. We only see a small tiny fraction of the true picture. So yes, from that perspective, the world is entirely momaya. Yeah, so good question, very good question. Okay, Rijit Banerjee says, what is quantum computing, and can it be used to encode the genes of an unborn baby? Quantum computing. So, quantum computing does a whole lot of stuff. See, quantum computing, a classical computer uses, I'll just make it as brief as possible. A classical computer, like your cell phone, your laptop, or whatever, these computers, classical computers, uh, they use something called bits uh, for storing information. A bit is either a one or a zero. Okay, that's what it is. It's a binary thing, binary digit, a bit. Uh, Classical computers, and these bits on classical computers, they are stored either in RAM or in some part of the memory. Okay, and they're manipulated using using gates. Okay, gates, superconducting gates. That's the architecture. I mean, that's a very rudimentary way of putting forth what the architecture is. In quantum computers, we have quantum bits. So let's say in a classical computer, we have a bit which is either a one or a zero. And if you have two bits, then you get these possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. Okay, that's the classical computer's possibilities with two bits. These are the four possible combinations of data information that you will have in these two bits. In a quantum computer, a qubit can be either one, it can be either zero, or it can be a superposition of one and zero at the same time. Okay, and if you have two qubits, then you have all those position, all those possibilities: 0, 0, 0, 1, 1, 0, 1, 1. All those possibilities exist simultaneously. Okay, that's one way of looking at it. And so that's the power. So you can exponentially increase the scale of your computations in a quantum computer, and then you take advantage of quantum properties such as superposition and entanglement and so on. Superposition is there, entanglement, wave function collapse, and much more. And you have you have quantum gates in quantum computers as opposed to classical superconducting gates. You have quantum gates, uh, and you have quantum algorithms like Shor's algorithm and Grover's algorithm, etc., etc., etc. So that essentially is how quantum computers operate. You need to keep the computing environment shockingly cold, as close to 0 Kelvin as possible. Otherwise, the superpositions will break down if any heat gets in, and you could have the introduction of noise and whatnot, which will destroy the superpositions and whatever entanglements you've created, and so on. And then you have quantum measurements through quantum traps and all that. I'll not get into all the technical stuff, but that's how a quantum computer works, and that's how it's different from a classical computer. And quantum computers have certain advantages, that they can perform certain computations in a finite amount of time that classical computers simply cannot do. So that's what a quantum computer is. Now, what are the applications of quantum computing, and where is a quantum computer superior to a classical computer? So there's a lot of applications, but you're speaking about genetics over here, right? Quantum computing and genetics of babies. So genomic data analysis is one application of quantum computing. Genomic sequencing data. When you do genomic sequencing, that generates massive amounts of data. Okay, all those for codes and whatnot. Okay, so quantum computers can process and analyze this data way faster than classical computers, which gives you much quicker, much more rapid insights into the genetic information that you're analyzing. And there's something called gene expression. Genes are expressed in under different conditions. Okay, and how specific genes are expressed, once again, you have to analyze massive amounts of data to sift through all the data and to express how the genetic expression happens. So once again, these complex patterns and correlations among all this massive amount of data can can be uh, can be unraveled, can be understood, can be recognized through quantum computers and quantum algorithms. It's very difficult to detect using classical methods because it will take way too long. Then you have something called gene networks. Genes don't operate in isolation. Okay, you have all this genetic information in your DNA, and genes don't operate in isolation. They operate in correlation with each other. They operate in complex networks. So quantum computing can hopefully help us unravel uh, these gene networks. These interactions are extremely complex, and classical computers probably just can't uh, you know unravel and analyze these. So quantum computers can probably do that, which will provide insights into how various genes influence each other and contribute to various traits and various immunities and various genetically inherited diseases and conditions and whatnot. And then there is evolution. So genetics and evolution go hand in hand. So quantum computers can help simulate various complex evolutionary processes, which help us understand how genetic traits evolve over multiple generations. Let's say 2000 generations. And how does genetic diversity arise within populations over, let's say, 2000 or 10,000 generations? You can simulate all that in a quantum computer. So that's what it is. So that's what quantum computers eventually will be able to do. Right now we are in the infancy of this. We are right now in the very beginning, the very infancy of quantum computing. So when it comes to encoding the genes of an unborn baby, I don't think that is ethical or even possible right now, because we have to first understand what I just all that stuff that I just outlined: gene networks and correlations and causation and so much more. Only then we will be in a position to safely, even think of safely encoding or editing genes. Obviously, today we have technologies like CRISPR, etc., which kind of help people to edit their own genes, which is very, very dangerous. And we already have GMOs, genetically modified organisms, typically crops and all that, but who knows what else is out there. So it's dangerous because we don't understand how changing one specific gene can affect everything else, because it's a gene network. It's not a gene in isolation, and it's evolved over millions of years. You just can't start playing God and tampering with things. So I would not want quantum computing to be used to create designer babies or any such thing. We have to, well, but my saying or not saying, or my cautioning over here will really not make much of a difference, unfortunately. But that's just how it is. So eventually, I'm sure quantum computing will be able to crack all of this, and possibly in the future, maybe 20 years, 30 years, maybe 5 years, maybe now, maybe uh, capable of telling you what to do, what modifications you may want to do, additions, deletions, modifications to the DNA and genes of organisms to bring about specific changes. It's possible, for sure. Ritik Pawar says, what is the technological singularity? How long will it take for us to reach the singularity after we reach AGI? I think AGI is the technological singularity. No, technological singularity means an artificial intelligence becoming self-aware. Self-aware. See, we are self-aware, aren't we? I know that I exist. I know that I am separate from my environment, and I know that I'm a player. I'm a participant in the grand scheme of things. I can actually, like Steve Jobs would say, make a dent in the universe through my actions, through causation and correlation. So I am aware of the fact that I exist, separate and individually from the rest of the universe. And every human being, as far as we can see, every human being is self-aware, starting from infancy. I mean, when do newborn infants, become self-aware? I'm sure pretty soon after they are born. We don't know exactly when, but it happens at a certain given time. We know that dogs and cats and various other animals are self-aware, and that kind of drags us into the realm of consciousness, which we'll not go into. So self-awareness is the key. So the technological singularity is when an artificially intelligent system becomes aware of its own existence. So right now we have these chatbots, uh, whatever these chatbots are, chat GPT and whatnot. They You can interact with them through text and various other means, and they talk to you like a human being, which means they have essentially passed the Turing test, more or less, and they seem to be self-aware. You ask it philosophical questions about itself, and it's going to respond to you in some ways, like a reasonably like a remarkably intelligent person, actually. But doesn't mean that it is actually self-aware. It looks like it's self-aware, but it's actually just, what these AI systems are right now. It's a whole bunch of neural networks, essentially equations, statistical equations. There's matrix multiplication going on at a massive scale and whatnot, and it's just giving you, these are systems that give you predictive output. What is the next best thing I mean, the next the most probable and the best possible next character of output? What is it that I can give you? And it's based on all this information and data that it has been trained on. So it's essentially just a statistical machine that seems to be very intelligent, and it's been trained in that manner. But I'm not sure if it's really self-aware right now. These AI systems like ChatGPT and Bard and whatever else is out there. But the technological singularity is when an AI system, artificially intelligent machine, becomes genuinely self-aware. Okay, and that probably is AGI, artificial general intelligence, or maybe at some point after we reach AGI. Uh, I don't know if that is even possible if it is even possible for an artificially intelligent system to become genuinely self-aware. How would we know it's become self-aware? I mean, right now these AI chatbots, they talk to us like they're self-aware. So how do we know it's actually self-aware? And what does it take for an AI system to become actually self-aware? So all that is right now very much under consideration. Some people allege that some of these AI systems have already become AGIs and self-aware and whatnot, but we don't know right now. So once again, when we talk about self-awareness, we're talking about this system becoming conscious of its own existence, consciousness once again. And it's possible that machines may never become conscious the way we are conscious. We have these sense organs that contribute to our consciousness. We have memory, and we have an internal representation of the outside external world within us, and that is kind of our worldview, and that kind of is our is the guidelines, it's a map that we use to chart our way around the world and so on. Do AI systems, are they capable of having that or not? These are big questions, existential questions, philosophical questions, because consciousness is philosophy. It's not science yet, because we don't have a definition of consciousness. So these questions are, we don't have clear answers to them, but we know that AI is very powerful already, and it's going to be way more powerful in the future. And we will have AI systems that are already way more powerful than we can imagine, but they are secret, because when a new technology emerges, it's typically the governments and the militaries that make first use of the full potential of the technology, the full capabilities of the technology. And what's put out there in the public domain is just a watered down version. So it's possible that AGI may already have happened, but does it mean that the system is conscious? We're not quite sure of yet. So the answer is we don't know right now. Okay, next question. Swapnil says, what is chaos theory? The butterfly effect. is it mathematically known as it is mathematically known as sensitive dependence on initial conditions. How applicable is it scientifically and in everyday life? Chaos theory. Chaos theory is all about so we talk about chaos theory and we give the metaphor of the butterfly effect. So what is a butterfly effect? Let's say I have a butterfly sitting in a garden in New Delhi, and the butterfly is fluttering its wings. And this little initial thing that happens, the butterfly is sitting on a flower and it flutters its wings and rises up in the air. So these are the initial conditions, and eventually it may end up causing a tornado in Lahore or in Rawalpindi or in Beijing, let's say, wherever. So that's the metaphor that we use to talk about chaos theory, the butterfly effect. Okay, so the sensitivity. So these are it's so chaos theory is essentially a branch of mathematics. Okay, it deals with systems that are extremely complex. They appear to be disordered systems, random systems, but they are actually governed by deterministic laws. Okay, so that's the branch of mathematics we're talking about, chaos theory. And these systems, and let's say we put a timer, we start a clock at time equal to t equal to 0, and then we go forward. So the initial conditions are the conditions that prevail in the system at time t equal to 0, and these systems are extremely sensitive to these initial conditions. Extremely large, extremely complex systems appear to be disordered, appear to be random, but they're governed by deterministic laws and highly sensitive to initial conditions, which means that very small changes that happen at the start, or very small things that happen at the start at time t equal to 0, can lead to vastly different outcomes. So in case the butterfly is fluttered its wings like this or like that, that would lead to vastly different outcomes. A tornado in Rawalpindi or a tornado in Shanghai, that sort of thing. Okay, so that is what it is. And we know, I mean, if you study the if you study gases, okay, the Boltzmann distribution and so on, then you will see that these systems are not really random and unpredictable. They are governed by deterministic these systems are actually deterministic, and you can statistically analyze them and you can predict what happens in the future. So that is what what this kind of system is. Okay, and even extremely small, infinitesimally small differences in initial conditions can lead to vastly different outcomes. And chaotic systems, there are examples like weather, this climate, uh, turbulence in fluids, in water. So all so many of these systems are governed by what's called non-linear equations, where the output is not directly or linearly proportional to the input. And this non-linearity of these non-linear equations that govern the systems, it is the key factor in the development of this chaotic behavior. So the study of weather patterns is one of the most well-known applications of chaos theory. Weather systems are chaotic. Okay, and that's why it's so hard to have accurate weather predictions, and such accurate weather predictions are only possible a few days in advance. And a very small change in atmospheric conditions can drastically alter weather patterns. So you need massive amounts of computation. You need supercomputers essentially to model the weather based on initial conditions. So weather prediction is a big it's a big application of chaos theory. Then there's application of chaos theory in biology and ecology, population dynamics, the fluctuation of species populations in an ecosystem. Let's take the whole of Africa. There are so many different species of animals and birds and aquatic creatures and insects and whatnot out there, and all of these are in a state of quasi equilibrium. But the fluctuations, but these species, their populations keep fluctuating based on a lot of different factors, so many different parameters. So chaos theory can help us in understanding these population fluctuations. Once again, very small, tiny changes in various environmental factors, like the amount of precipitation in a certain region, or the temperature of the climate in a certain region, whether it was raining or snowing, or whether there was a hailstorm or whatever. That can lead to massive, drastic variations in the sizes of populations and and the fates of various populations of species. So that's another application. Then we have fluid dynamics, like I said, electrical circuits, mechanical systems. All of that can be used. There's the application of chaos theory and all that. Uh, there's economics and finance. So financial markets are chaotic. They exhibit chaotic behavior, and very small changes in investor sentiment and external economic factors can lead to significant fluctuations in stock prices and market trends. So many applications of chaos theory. Human behavior can be influenced by chaotic dynamics. uh, Very small changes in environmental circumstances or individual circumstances can lead to significant changes in human behavior and decision making. So once again, that is this applications of chaos theory there. Then in health, in medicine, chaos theory can help you understand the uh, cardiac arrhythmias and epilepsy. So epilepsy is all about brain waves, and chaotic brain waves causes epileptic seizures. And when it comes to cardiac arrhythmias, that is deviation from the steady harmonic pattern of your heartbeats. So when you have irregularities, that is also kind of chaotic. So these are also chaotic systems, the brain waves, the heart, lung system, and all that. So all of this has chaos theory applications. So yeah, so that's kind of application of chaos theory in everyday life. Stock markets, definitely everyday life. uh, Weather patterns, definitely everyday life. Human behavior, very much everyday life, right? And yeah, in certain diseases, certain conditions like epilepsy, cardiac arrhythmias, and I'm sure there are so many more applications, but I can give you a few right now. There you have it. Good question. I like it. Like it. Yes. Good question. Okay. Rajorshi says, how does a butterfly retain its memory as a caterpillar even after getting most of itself digested apart from a few cells? Can this be researched and used to transfer memory in humans? So butterflies begin as caterpillars. We know that, and then they enter this cocoon phase in which they create this silk cocoon and ensconce themselves in these silk cocoons, and then they go through a chrysalis phase and whatnot, and then they emerge as butterflies, right? So the end product, the butterfly, is so visibly different, structurally and architecturally different from the initial product, the caterpillar, right? So different. But it's the same organism. And the question is, how does a butterfly retain its memory as a caterpillar after undergoing this massive transformation, this metamorphosis? And maybe much of it gets digested apart from a few cells. I'm not sure about that, but what happens? The question I want to ask is, how do we know that a butterfly has any memory of its past life as a caterpillar? How do we know that? I mean, has anybody mapped the brain of a butterfly and done a one-to-one correspondence with the memories that were there in its brain when it was a caterpillar? And do those memories persist? We don't know that. We don't know. And it's very hard to understand how memory works in brains. If you want to just map a cubic millimeter of human brain, the data output of the data that comes out of it is several terabytes or petabytes. I think it's terabytes, like a few hundred terabytes out of a single cubic millimeter of human brain. And a cubic millimeter of brain, I'm not sure how large a butterfly's brain is. I'm sure it's less than a cubic millimeter, or maybe around a cubic millimeter. I'm not sure. But that too is a tremendous amount of information. How do we map which memory is where? We still aren't there. We still don't have the capability of knowing which memory is located in which specific physical location in a brain, and in what form the memory is stored. It's through neural connections and all. We still don't have the capability or the understanding of this. So we don't know if butterflies, when they emerge out of the cocoons, have any memory of their past life as a caterpillar. Okay, we don't know. We have no knowledge at all, as far as I know. If I'm wrong, please let me know in the comments below, and show me some references, and I'll be happy to educate myself. But as far as I know, we don't have the understanding of this at all. And yeah, there's this philosophical concept called the ship of Theseus, right? If you have a ship made of wood, and the ship goes out on voyages, and over time it has wear and tear, and you have to start replacing the various components of the ship from time to time. And after, let's say, 50 years or 100 years, the ship still exists, but all the components have been replaced. Everything has been replaced. So 100 years ago, whatever the ship was made of, today it's all different materials. What is this? Is it so? The question is it the same ship, or is it a different ship altogether now? It has the same size, the same shape, the same appearance, but everything has been replaced. So, is it the same ship, or is it a different ship? And that applies to us also, because all of our cells keep getting replenished. Cells die, and cells are reformed and reborn, and all that. So, are we the same people? Am I the same person I was, let's say, a decade ago? I think I am, and so on. So, yeah, these questions, they bring in philosophical musings as well. But the answer is, we don't know what memories a butterfly has when it emerges as a butterfly. Does it have any memories of its past life, of its previous phase of existence as a caterpillar? We don't know about that. We don't know. Pradyumna says, what is string theory? String theory is an interesting question. String theory. A much maligned branch of physics is string theory, isn't it? So string theory. So it's like this. In standard physics, we talk about electrons, we talk about protons, we talk about neutrons, we talk about electrons, and so on. These fundamental particles, quarks, and all. And we represent these particles as points. Okay, point particles. In Newtonian physics, in the kinetic theory of gases, and even in particle physics, we look upon these elementary particles and etc. as point particles. Okay, so that is how standard physics or classical and quantum physics looks at particles, as point particles. But in string theory, we don't look at particles as point particles. We look upon them uh, as vibrations of strings. Okay, so and the vibration of strings, the different ways in which strings vibrate, one dimensional strings vibrate, these vibrations give rise to different kinds of particles. So that's the basis of string theory. It doesn't, the fundamental building block of string theory is not your zero dimensional point particles, but one dimensional strings, and these strings vibrating strings. So like a guitar string, if you play a guitar string with which in there are different ways in which these strings vibrate. And so if these are your strings of string theory, these vibrations of different modes, they give rise to different kinds of elementary particles. Now, string theory has space time, but very different space time from what we have in general relativity. In general relativity, we have four dimensional space time, three dimensions of space and one dimension of time. In superstring theory, we have 10 dimensional space time. So one dimension of time and 9 dimensions of space, the three dimensions that we are aware of, and 6 more dimensions of space that are highly compactified. So they are highly curled up, and we are not able to visualize them. We cannot see them, but they exist, and they're extremely compact dimensions. That's why we are oblivious to their existence. So that's superstring theory, 10 dimensional space-time. There's something called M theory, which has 11 dimensional space-time. Then there's bosonic string theory, which has 26 dimensional space-time. Okay, and in addition to strings, in string theory, we also have higher dimensional objects called membranes, or brains in short, BRANE, brain. And these brains can be of various dimensions, like a two-dimensional surface or a three-dimensional volume, and strings can attach to these brains. And string theory also involves a principle called supersymmetry. And according to supersymmetry, every particle, every fundamental elementary particle has a super partner with a different set of spin properties, with different spin properties. And this helps solve certain theoretical issues, but we have never observed any super partners or super particles, squarks, or whatever else, photons, electrons. We haven't observed any superpartners uh, ever. I mean, it was the great hope that the Large Hadron Collider would bring forth evidence for supersymmetry, but sadly, unfortunately, that has not happened. Okay, so that is what string theory is in a nutshell, and there are big problems with string theory. This theory has been around for decades, since the 1950s, 1960s, 60s probably. One of the glaring challenge that string theory faces is the lack of direct experimental evidence. It has not it has not made any predictions that are experimentally observed or provable, falsifiable. So string theory is not falsifiable. Okay, so the physical scales at which the string theory operates are much smaller than the scale of an atom, and the reach of our experimental capabilities. So even if it makes any predictions, they cannot be experimentally verified or falsified. So that's one of the major problems that you face with string theory. And then there's the mathematical complexity. The string theory is highly mathematical, extremely complex, lots of different versions, and finding solutions that describe our universe accurately is difficult. Thus far it's proven to be impossible, which brings us to the landscape problem. The string theory landscape, the string theory multiverse, so to say. The string theory allows for a tremendously large number of possible solutions or universes. Okay, it gives a tremendously large number of possible solutions. This is called the string theory landscape, and each of the solutions corresponds to a possible physical universe with different physical laws. So each universe has unique set of physical laws, and no two universes are the same. And there are 10 raised to, I don't know, 500 or so such possible universes. That's the string theory landscape of the string theory multiverse, which makes it essentially impossible to determine which of the solutions describes our universe, and so on and so forth. So these are the problems that string theory faces. It's not solved any of our problems. The grand objective of string theory was to give us a quantum theory of gravity. And thus far it's not really. I mean, yeah, it's wonderful mathematics and all, but it's not solved any of our problems. So maybe we need to look beyond string theory. All right, that's what. Okay, Rohan Vidi says, to understand the beginning of the universe, we rely on the radiation reaching us from back then. Yes. Since there was no radiation prior to the Big Bang, or if there was and it cannot reach us, do you think it's impossible for us to know conclusively what caused the Big Bang? This is a great question. So typically people will ask, what caused the Big Bang? Right? But this is a better question, because this Rohan over here understands how science works. We need evidence to form theories. So what the standard model of cosmology, the Big Bang model, it's all based on experimental observable evidence, right? We have the cosmic microwave background radiation and so many other aspects that go into this, and all of that creates the standard model of the lambda CDM model, the cosmological model, Big Bang theory model. So to understand the early phases, the early era of our universe, we need data from that time. So we have to rely on the radiation from that time period. And there was no radiation before the Big Bang. We know that. So there's no data from that time, from before the Big Bang. And even the first few instants after the Big Bang, before inflation happened, when all four forces were unified, most likely into a grand unified force, and then there was symmetry breaking. It is believed to have happened, and then the forces decoupled one after the other. I mean, of that also, we don't really have a great amount of evidence for that. Uh, so your question is very valid, and the answer is what you're suggesting it is. It's impossible for us to know conclusively what caused the Big Bang as of today. As of today, we don't have any information about that period of time, the very beginning of time itself, right? Obviously, there would have been gravitational waves from that time. Space time existed, and space time was squeezed into this essentially almost a point. And so space-time existed, and then something caused space-time to expand. It was not an explosion, it was expansion. And you would have had gravitational interactions of various kinds. Initially it was just pure energy, probably pure energy. What form would the energy have taken? Would it be photons or whatnot? And at some point in time in the very early universe, gravitational waves would have uh, emerged. And if we can detect those, that relic gravitational radiation, then that may give us a better insight than we currently have about the very initial conditions of the universe. But overall, what you're saying is right. We don't have There would be no radiation of any kind prior to the Big Bang, which essentially means that we will not be able to know what happened at that time and what caused the Big Bang. So yeah, as of today, it's impossible for us as of today to know what caused the Big Bang, and that is correct. Okay, Rohan again says, what's the difference between a supermassive black hole at the center of a galaxy and an active galactic nucleus or active galactic nuclei? So we know that most galaxies have a supermassive black hole at the center. Now, supermassive black holes are black holes, but they are very massive, like supermassive. The name itself suggests how large they are. So a supermassive black hole can have a million solar masses, million times the mass of the sun, or maybe several billions of solar masses, several billion times the mass of the sun. Um, and we know that the Milky Way has the Sagittarius A star supermassive black hole, which is a few million solar masses, not a very large uh, supermassive black hole, reasonably small sized supermassive black hole, and there are much bigger ones. So that's your standard supermassive black hole, which is at the heart of most galaxies. Okay, at the center of most galaxies. Now there's something called an active galactic nucleus, AGN. So these are active supermassive black holes. What do I mean by active? So when it comes to active galactic nuclei, these supermassive black holes are actively feeding. They're eating. What are they eating? They they're eating material, matter, essentially gas and dust. Gas and dust. So these active galactic nuclei have gigantic accretion clouds around them. This big tornado whirlpool like situation, all of this gas and dust falling towards a black hole with high angular momentum, extremely high velocities, and relativistic velocities, not exactly close to the speed of light, but let's say half the speed of light, or you know velocities at which relativistic effects become visible and apparent. So relativistic velocities, extremely high velocities at which this gas and dust is being sucked into the black hole. And very close to the black hole, there's this massive traffic jam of matter which becomes extremely luminous, extremely hot. And much of the energy of these infalling particles gets converted into gravitational energy. And then these black holes, they are also rotating, and the cloud is also rotating. And at the two poles of the black hole, there's the emission of jets, relativistic jets, extremely highly luminous jets of relativistic particles. So let's go to Google and look at let's say an artist's representation of an active galactic nucleus. Active galactic nuclei. Um, yeah, so that's what it looks like typically, and we actually have images of jets. Here's one. Here's a good image of an actual jet that's being thrown out of an active galactic nucleus. So this is what it looks like. All right, and the polar regions of the black hole emit these relativistic jets, extremely high energy, high velocity jets of charged particles, and that's what it is. Uh, an active galactic nuclei, if they're extremely luminous, they are called quasars. Uh, and there are other categories of these things as well. If the jets are coming directly towards the Earth, these objects are called blazars because they blaze forth and so on. So yeah, that's what it is. So that's the difference between a standard supermassive black hole that is living its life and minding its own business quietly, not bothering anybody, and an active galactic nucleus that's like telling everybody, "Hey, here I am," and you better, say. So that's what it is. Okay. Gabc 2778 says, fun question. We may soon be in the age of exploration, space exploration, and we may see humans on Mars in 2050. Okay. What are your thoughts on life once existing on Mars? And hypothetically, let's say there was life on Mars, but similar to the dinosaurs, they are now fossils, but we haven't discovered it yet. If we find fossils on Mars, how much of a dramatic change will that be? To the age-old question of are we alone, and also your thoughts on the idea of God being man-made. Will it further entice us to keep exploring space? Okay, let's talk about life on Mars. There are lots of questions in here. We cannot unpack all of these. So yeah, eventually, hopefully, if things go well, we will have humans on Mars by the 2040s, perhaps 2030s, maybe 2040s, and definitely, hopefully, 2050s. Okay, so we will have humans there. What are my thoughts on life possibly existing on Mars in the past? It's possible. Mars was a very Earth-like planet a couple of billion years ago. We know that there was a tremendous amount of flowing water on the surface of Mars. Mars had a much thicker atmosphere in the past, and uh, and it's possible there was life on the planet. So if it was warm enough to have liquid water, flowing water, oceans and lakes and rivers of water, and this went on for a very long time, then yes, it's possible that life may have emerged on Mars, maybe independently of life emerging on Earth. And there are some speculative questions, right? We have discovered certain Mars origin meteorites on Earth, and when the cross sections were taken and examined through microscopes, certain artifacts are visible, like which look like fossilized bacteria. What's the name of that Mars asteroid? ALH something or the other. Shall we put that on the screen? I mean, let's quickly take a look at that. Once again, our friend Google, Mars meteorite ALH. Yeah, 84001. That's the one. Come on. So let's take a look at the electron microscope image. And you can see what looks like a tubular object that could be a proto microorganism or something like that. So this isn't a conclusive evidence of life having existed on Mars in the past, but it's a telltale sign. As you can see, there are lots of these structures that look like microorganisms, fossilized microorganisms. Here's another image of that, and so on. So it's possible. So it is definitely possible that life may have existed on Mars in the past. Maybe, like you said, dinosaurs. I'm not sure, but dinosaurs. It's quite possible that uh, microbial life may have existed on Mars, and maybe more advanced life forms as well. But we don't have any evidence of that. So once we have humans there, they could do some digging or whatever, and maybe they will discover something. It's possible. I'm open to the possibility. I'll be happy if we discover that. And obviously, if we discover that, that will be a fundamental revision of the way we look at the universe. It will prove that yes, if we discover that on Mars, that it will prove that life isn't unique to Earth. It existed on Mars in the past. Maybe it still exists underground. Possible. Yeah. So we will get answers to these questions eventually once we reach there. So yeah, it's interesting. It's exciting. That's why space exploration is really exciting, because it gives us answers to so many questions, and it broadens our horizons, and we understand the world, the universe much better. At least our neighboring planet. First of all, we can start with that, right? Samrat Chakraborty says, since Mars lacks a magnetosphere, will it ever be possible to terraform it into a planet like Earth? And can we create an artificial magnetosphere by running huge electric strips around across the circumference of the planet? Okay, what is a planet's magnetosphere? Earth, our planet, our home planet, has a magnetosphere. It's this magnetic field that is generated by through the dynamo effect in the internal through the internal structure of the Earth, which is molten iron and nickel. And if you want to see a cross section of the Earth, let's once again go back to the images. Earth cross section. And if we look in this, we have, let's take a look at this image. So we have the crust that we are familiar with, then we have the upper crust, the lower crust. There's the mantle, and then there is the lower mantle, there's the inner core, there's the outer core, and all that. So there is a gigantic magma layer, and then there is the inner core, which is molten, the external core, which is molten metal, liquid iron and nickel, and then there's a solid uh, inner core. So it is so this molten metal swirls around, and there are currents and eddies within it, and it is likely that it is highly charged. There are charged particles, there are ions in there, and that is what creates causes the dynamo effect and creates the magnetic field of the Earth. So the Earth is a large planet compared to Mars. The Earth's radius is much greater than that of Mars. So we know what is the formula for the volume of a sphere. Planets are not entirely spherical, but we can approximate them as being spheres. The formula for the volume of a sphere is 4 by 3 pi r cubed, where r is cubed. And the formula for the surface area of a sphere is 4 pi r squared, where r is squared. So the larger r is, the smaller is the surface to volume ratio, and the smaller r is, the larger is the surface to volume ratio. Do the calculations, okay? So when you have a small planet, the surface to volume ratio is larger, which means that the internal part of the planet, the inner, whatever molten hot part of the planet, will cool faster. All the planets that we know of have heat within them inside that is left over from the birth of the solar system, when everything was just hot. So Mars cooled faster than Earth, and that's why the liquid metal part of Mars must be more or less almost solid by now, which is why it has a very weak magnetic field. And because it has a very weak or non-existent magnetic field, what that did is that charged particles, solar wind, started impacting the atmosphere of Mars directly, and eventually they ionized the atmosphere and stripped most of it away. And that's why Mars has a very thin, wispy, tenuous atmosphere compared to the Earth, because this process happened over more than 1 billion years of time. And that's also the reason why it stripped away the water from the surface of the planet. So all the water that exists on Mars is underground or in the polar regions. So yeah, that's what happened in Mars. Now Mars lacks a magnetosphere. Will it be possible to terraform Mars? It is possible to terraform Mars over a period of, let's say, 1,000 years. Okay, to be realistic. So we terraform Mars, we give it a thick atmosphere, and we increase the temperature of the planet, of the atmosphere, to reasonably Earth-like levels, and we ensure there is flowing water again on the surface of Mars, and there are lakes and rivers and oceans and all that. We can do that through a variety of means. I'll not go into the means. One of the silliest things is nuke Mars. Well, that's also a dirty way of doing it, but not advisable. So let's say we terraform Mars, then what happens? The planet doesn't have a magnetosphere. So is it worth doing it? Look, the process of the stripping away of the atmosphere because of the lack of the magnetosphere, this process took about 1 billion years. 1 billion with a B. We're going to terraform Mars in 1,000 years. And for us, 1,000 years is a tremendous amount of time. For us, 100 years is a long time, isn't it? And if you look at known human history, it's about 10,000 years old. And nothing's going to happen in 10,000 years. So it's definitely worthwhile terraforming the planet. And this, if we make it more Earth-like in 1,000 years, that will last for at least a few 100,000 years. So it makes a lot of sense to do that. And creating an artificial magnetosphere by running huge electric strips, it's extremely unfeasible, because you will need gigantic electric currents and gigantic electric charges. There are a tremendous amount of metal to do that, and it's not practical to do that. So creating an artificial magnetosphere in this manner is impractical, but it is definitely worthwhile terraforming the planet and having the planet being Earth-like for a few 100,000 years. That would be great. Okay, Amit Joshi says, recently human experiments have begun at Neuralink. Where do you see this going? Could this be a threat to humans? Could it affect freedom of thoughts? Thank you. Uh, yes, Neuralink is in the process of conducting human trials. At least one test subject has been announced, and that person is a quadriplegic, which means that that person has lost the ability to control his or her limbs because of paralysis or whatever. And Neuralink has made apparently a big difference in that person's life. Uh, so what is Neuralink? It's essentially a chip that's inserted in the brain. It's implanted into the brain matter, and it can perform a variety of functions like injecting data directly into your brain, interfacing the brain directly with computers, external computers. So you can just sit like this, cross your arms, and control your mouse cursor or your smartphone or your tablet just through your thoughts. And you'll be able to play YouTube videos in your mind. Eventually, you'll be able to watch movies with your eyes closed in your mind, download music up. I don't know, anything's possible. So is this a potential threat for humans? Yes, in the future it could be a threat. You could use it for a variety of things. You could, if everybody has a Neuralink or some kind of chip implanted, you could cripple human brains by injecting garbage data into them, or you know, impacting certain functions of the brain, maybe even causing a stroke, maybe even shutting down somebody's heart. Anything's possible down the line, right? I'm not saying Neuralink is doing any of that. Neuralink, I'm sure, has, well, at least the stated objective is to make a difference, a difference for the good for humanity. But this technology, any technology, has multiple uses. Every technology is a double-edged sword. Nuclear technology can be used for good as well as for bad. A stick can be used for good as well as for bad, and so on. So this technology could end up opening a Pandora's box, as any new technology can, like AI can, for example. So yes, it could even affect the freedom of thought. Who knows? Yatharth Chaturvedi says, have you seen the new versions of OpenAI's and Google's new AI models? Should we be worried, and what do you think this will do in the future? I haven't seen all the latest versions. There are so many AIs out there. There is Claude, there is Bard, there is Greg. I don't know what it's called. There is Chat GPT, and I don't know how many other models are out there. I haven't seen all of them. I've seen maybe one or two. Uh, should we be worried? Well, it's definitely something that could be used to a great to do a great amount of good, to do a great amount of harm, to control humanity, to monitor humanity, to supervise humanity. A lot, a lot. So it's kind of scary. It's possibly very dangerous, and it could, even if the AI system doesn't become self-aware and conscious, and even if it doesn't become an artificial general intelligence, it will give a tremendous amount of power in the hands of those who wield these systems, the ones who control and own these systems. So the AI system doesn't need to be self-aware and super intelligent and all that. It doesn't need to be an AGI. It already has enough power to completely change the future course of humanity. I mean, right now, the lowest level impact we're thinking of is that jobs will become obsolete, professions will become obsolete, data entry professions. The data entry profession will become obsolete. Fact checking will become obsolete. Proofreading will become obsolete. Uh, Research assistants will go out of business. Digital artists, musicians will go out of business. So many things, so many skill sets are becoming redundant. That's the lowest level impact. But there are many more high level impacts of artificial intelligence, like, it could control people's thoughts and beliefs and narratives that they believe in. Every person could eventually be given a tailored version of the news that they're not even aware of, that everybody else is getting their own specific tailored version of news. So news will come in flavors, books will come in flavors. Everybody will have books written specifically for them on demand. Music will come in according to your tastes, and it will essentially create all these divergent human beings who are not even aware of what's happening in the world. That's one version of what could happen, and much more. It could give rise to super intelligent robots, armies of robots. So all warfare could be all future warfare could be AIs and robots fighting each other and possibly attacking humans also. Yeah, that's the Terminator scenario, isn't it? And so on. So yeah, there are so many dangerous possibilities and scary possibilities in the future. That is indeed true. Aviral Chauhan says, "What are your thoughts on Oumuamua? Was this a comet or an extraterrestrial piece of technology? Similarly, how can Black Knight be space junk when no country has capabilities to launch satellites at the time? Are these just hoaxes or there's some truth to them? I have no idea what Black Knight is. I've heard some rumors. I've not looked into it. So I cannot answer the question about Black Knight. Oumuamua. Okay, so Oumuamua is this object, space rock, looks like, or space thing. Okay, that was discovered a few years ago, and it was traveling at a very high speed, a very high velocity, and its trajectory was hyperbolic. It wasn't parabolic. A parabola is a closed loop. A hyperbola is an open loop. So it went around the sun, and it went off at very high velocity in a hyperbolic trajectory, which means it's on a trajectory that will lead it out of the solar system. It's gonna go out. It's gonna escape. It's on an escape path with an escape velocity. Okay, which means that it came from outside. It wasn't born in the solar system. So it's an object. It's an interstellar object which came from outside, and it's on the way back outside. And it's right now, I don't know where it is, but it's still within the solar system. It's going to be within the solar system for a few decades more. And it had certain interesting characteristics. Uh, it was highly reflective, almost like a solar shield or something, almost like it was made of polished metal. That's that sort of reflectivity, apparently. Okay. And it is said that it changed velocity over time. So it did not travel with a standard, you know, hyperbolic trajectory with the standard velocity. You can calculate the velocity of an object like that, but it actually changed its velocity. It sped up over time at a certain phase of its trajectory. So that is kind of well, that kind of would indicate, if it is true, that it had some propulsion on it. It was able to change its velocity. So I believe it is the astrophysicist Avi Loeb who's said that this was most likely alien technology. But do we have evidence of it? Apart from whatever we have measured briefly and rudimentarily, we don't have much more evidence. So there is a proposal that we could send a spacecraft to catch up with this object, Oumuamua, in the next 20 or so years, when it will be maybe somewhere around the vicinity of the gas giants, those orbits. So by 2050 or so, if we launch a spacecraft by, let's say, 2030, we can have it catch up with Oumuamua by about 2050, in 20 years or so, in 2 decades. If we do that, then we'll be able to get a better idea, a proper idea of what this object really is. But beyond that, as of today, we cannot say much beyond speculating based on whatever data is available. Samrat says, Why do volcanoes occur on islands? Do volcanoes form in mainlands too? Yes, it's not just islands. Yeah, there are lots of volcanoes on islands. Japan is a bunch of islands. It's an island nation, and there are lots of volcanoes on Japanese territory. If you look at Sakhalin, if you look at the Kamchatka Peninsula and so on, there are lots of volcanoes there. There's lots of volcanoes in Indonesia, which is islands. Then there are a couple of volcanoes in the Andaman Islands region, the Narakondam and the Barren Island volcanoes. One of these is active or somewhat active, not dormant. Then you have the Greek islands. There is Santorini, which is a volcano. Then you have Egypt. You have Italy, which is kind of part of this region. It has Mount Etna, Mount Vesuvius, and so on. And there's a bunch of volcanoes in South America: Aconcagua, Popocatépetl, and so on. I think Aconcagua is a volcano. I think is Aconcagua a volcano. Let's just double check that, is Aconcagua. Aconcagua. Is it volcano? Is it a volcano? Okay, is Aconcagua a volcano? I think it is. Okay, it used to be an active stratovolcano long ago, and it's now probably a dormant volcano. Okay, so Aconcagua is one. Uh, Popocatépetl. That's another stratovolcano. It seems to be active, and so on. So you have these volcanoes like Aconcagua, Popocatépetl, which are not on islands. These are very much on what you call the mainland. And there's many more. Where is Aconcagua? Popocatépetl is in Mexico. Aconcagua. All right, we'll have to zoom out to discover where it is. Okay, it's in Chile, Aconcagua. And there's more. There's more of these things. Okay, there's more of these volcanoes, and then you have volcanoes in the U.S. as well. What is it called? USA volcano. Let's just type USA volcano. So Yellowstone is this giant super volcano, and there's Mount. What is it? Rainier? Was Mount Rainier a volcano? Nah. And so on. So I'll not waste your time by looking at different volcanoes over here. The point is that you have volcanoes on islands. You also have volcanoes on mainland. Now, why are volcanoes? What is the cause of volcanoes? Volcanoes typically occur in parts of the Earth where there is a defect in the crust of the Earth, and the magma is able to come out. So that is typically when you have the junction of different tectonic plates. So you have tectonic plates, the subduction of one tectonic plate going under the other, and these are also earthquake zones. So there's something called the Ring of Fire, the Japan, Indonesia, and Andaman region, where you have so many volcanoes and so many earthquakes and so on. So volcanoes occur because of defects in the earth crust, where you have tectonic activity, tectonic plates either going rubbing against each other, or going below going below the other. That's where you have these that's where the magma has the opportunity to come out, and that's what causes volcanism. And that can also happen on mainlands, but more on islands and more at the intersection of these tectonic plates. Okay, AD Guru Prasad says, what does the word dust cloud mean, which was the thing that formed our solar system? It cannot be the dust that we see on Earth. Okay, so our solar system was formed out of what we call a solar nebula. So initially it was a solar nebula, and it formed a protostellar disk, and that eventually gave rise to the sun and all the planets. So what was the composition of this solar nebula? This solar nebula was primarily composed of just gas. And what gas? Primarily hydrogen and helium, which are the two most abundant elements of the universe. And there were trace amounts of other elements like silicon and oxygen and carbon, iron and whatnot, other heavier elements. Okay, but the gas was just hydrogen and helium, and the dust was these tiny solar particles made of these elements like silicon, iron, oxygen, carbon, and other heavier elements, like I just said. So there was gas and there was dust, and all of this together made up the solar nebula. So these particles, this gas and this dust, it originated from previous generations of stars that had already gone through their life cycles and died and ejected all this material into space. So that was the origin of this stellar or solar nebula made of gas and made of dust. So it's not the dust that we find on the Earth, it is these tiny solid particles made of these elements that were born in the furnace, in the hearts of older stars. So the sun is a reincarnated star, and it formed out of this large nebula, this large molecular cloud, and this molecular cloud, this nebula, most likely experienced some kind of disturbance, like a shock wave from a neighboring supernova or something like that, which caused it to collapse under its own gravity. And that's how the sun and these other planets, etc., were born. And these dust particles that you're referring to were the building blocks of the terrestrial planets: Mercury, Venus, Earth, and Mars. And they were also the building blocks of the cores of the gas giants. Which are the gas giants? Jupiter, Saturn, Uranus, and Neptune. So yeah, that's what it is. So that's the gas, that's the dust cloud that you're mentioning. It was not just the dust cloud; it was a cloud made of hydrogen, helium, and all these uh, particles of these various elements. OMGABC, etc. Are the chances of intelligent life existing on a planet similar to Earth just a chance of probability? Let's assume life exists on an Earth-like planet, but are the chances of an intelligent species such as humans just a probabilistic chance? Because our close relatives like the Neanderthals died out, we have gotten very lucky surviving for thousands of years. Like I mentioned earlier, uh, there are these great filters that every species, every intelligent species has to go through. For us to exist today, lots of things had to go right. Life had to somehow emerge on the planet, and we don't know how it emerged. Then it had to go from cellular to multicellular life forms. Then these life forms had to survive multiple extinction events. They had to emerge out of the oceans and onto the dry land, and then they had to evolve in a variety of ways. They had to survive the Chicxulub impact event 66 million years ago that killed off the non-avian dinosaurs. Then the life form had to become bipedal and become more intelligent, and then survive lots of extinctions like the extinction of Homo habilis, Homo erectus, Homo neanderthalis, and then Homo sapiens survives, and who knows what other problems we will see in the future. Nuclear war is a dangerous possibility, climate change, and more extinction events, more meteors or comets, asteroids coming in, and so on. So the chances are very slim. But since you have so many stars and planets out there in the observable universe, more than 10 raised to 21, it would make sense that there is intelligent life out there. And then the question arises, where is it? And we don't know. So maybe it's a probabilistic chance that it just somehow emerged. We don't know how life emerged. We know that every life form on this planet, whether it is multicellular beings like us, whether it is microorganisms like water bears, whether it is bacteria, unicellular organisms, whether it's even viruses, all of these organisms have DNA. Now, DNA is an extraordinarily complex molecule. It just doesn't just spontaneously emerge. So the question is, where did it come from? How did something like this evolve? And extremely, even the simplest microorganisms have such incredibly complicated DNA. Simpler than ours, but still more very complicated. How does a molecule like that evolve, and how does it develop the ability to replicate and jump inside these bags, these membranes called cells, and develop all the organelles, the Golgi bodies, the mitochondria, the endoplasmic reticulum, and whatnot, cilia? How does all this happen? How does this happen in just 4 billion years, 4.5 billion years? And when first life that emerged was unicellular, it emerged about 3.7 billion years before today, which is less than a billion years after the Earth was born. How did such complex life emerge in just less than a billion years? So we don't have answers to these questions. So maybe it's chance, maybe there was seeding somehow on our planet through some mechanism. We don't know. So there are lots of questions we can't answer right now. Preetam Sharma says, maybe a rookie question, not an issue. You can ask rookie questions. So we see photographs of various nebulas, stars, also the first ever black hole image. How do we capture them? Which spectra waves do we capture? How does it work? Okay. When we see images of galaxies, we typically use visible light telescopes. So these telescopes give us images in visible light, the kind of light our eyes can see in the visible part of the electromagnetic spectrum. Then, so most of the stars, galaxies, nebulas, planets, whatever we see, whatever images we see, are generally taken with Earth-based telescopes or the Hubble Space Telescope, which all see things in the visible spectrum. Then you have the Chandra X-ray Observatory, which takes images in the X-ray spectrum. That's something we can't see, but yeah, it gives you a different view of the world. And then you have something like the JWST, the James Webb Space Telescope, that looks at the universe in the infrared part of the spectrum. It shows us, it detects the oldest light. Okay, the light that is the most stretched out because of the expansion of the universe and so on. So we use these different parts of the spectrum. We use different instruments that can access different parts of the spectrum to form this image of various parts of the universe, various components of the universe. And that's how we discover more things about how the universe evolved and how we came to be the way we are right now. What about the black hole image? So the image, okay, let's go to Google once again. M87 image. Okay, this one. So this is the image of the M87 supermassive black hole. Let's put this on the screen. This is the original one, very diffuse, and this seems to be a improved one, if I'm not mistaken, in polarized light. And you can see the fine structure, so to say. Yeah. So how was this image taken? Does it actually show the black hole? It does not show the black hole. It shows the accretion disk and the magnetic lines and the magnetic lines of force, almost, you could say. So this is not an image of a black hole. This is the image of the accretion disk around the black hole, the glowing accretion disk. And you can see there's this central darkness, which is the actual black hole. And there are relativistic effects over here, which means that there's a lot of curvature, bending of light, and all that. And it once again turns out that it is exactly in line with what general relativity says. So the black hole image was also taken in which, I don't remember which wavelength it was taken in. Visible light, was it, or was it millimeter length waves? I don't remember right now. Doesn't matter. But yeah, so to look at the image, to look at the universe, you can use different parts of the electromagnetic spectrum to get different kinds of information. And that's how it works. Okay, user DJ something or the other says, can quantum mechanics explain consciousness? Quantum mechanics and consciousness. Look, we don't know if quantum mechanics can explain consciousness. First of all, we don't have a clear definition of consciousness. You ask a biologist, you ask a neuroscientist, you ask a neurologist, you ask an information theorist, you ask a physicist, they will all give you different they will all attempt to define consciousness in different ways, and nobody will be able to actually properly define consciousness. So we don't have a definition of consciousness, first of all, which means that the consciousness is currently not a subject of scientific inquiry, it's a subject of philosophical inquiry, because there's no scientific definition. First of all, we don't know what consciousness is. If I have a system, a black box, how do I know there's a consciousness inside? What are the characteristics that it would exhibit that would tell me it's conscious? It's kind of asking the question, what is life? What's the definition of life? We don't even have a clear definition of life. When we see life, we know it's life, but can we define it? There is a certain set of definitions, but it's still not, it's kind of vague. I mean, take a virus. A virus is kind of on the dividing line between alive and not alive. It exhibits some qualities, some properties of crystals, but it also has DNA. It also has self-replication or assisted replication, but it doesn't exist in homeostasis with its environment. It doesn't affect or modify the environment. It just exists. So it's difficult to even define life. Similarly, it's difficult to, it's right now it's impossible to define consciousness. Then when there's a phenomenon that you don't have a definition for, then how can quantum mechanics, which is science, explain that? And then, of course, there are attempts to do that. There is the OR theory of Hammerhoff and Penrose that says that the microtubules that are inside your brain, you can sustain quantum superpositions, etc., in these microtubules, and that could be the basis of consciousness. That's one theory. Do we have evidence and proof of that? Not sure we do. So there are attempts that are being made to see if consciousness can be explained via quantum mechanics. The Hameroff-Penrose theory is definitely in line with that. It says that these microtubules, they can sustain quantum superpositions within them. Once again, the brain is a wet, warm environment, and decoherence would happen very readily in there. So there's a question about whether it's possible. And then there's the question of what is consciousness an emergent phenomenon? Does it emerge out of complexity? Does it emerge out of low entropy states in highly complex systems and so on? We don't have any of the answers right now. So we can't say for sure whether quantum mechanics can explain consciousness or not. Okay, Curious Prabhat says, what's the bootstrap paradox? Please explain. Have you heard of the grandfather paradox? Okay, there's this hypothetical evil guy, very evil guy, okay, very, very bad guy. He makes a time machine. He goes back in time 80 years. He locates his grandfather and kills his grandfather. Okay, then, so the grandfather and he kills the grandfather when the grandfather was still a kid. So the guy goes back in time, kills his own grandfather before his grandfather was able to produce any children. Then how does he exist? So how does the killer exist if he is able to go back in time and kill the grandfather, who is the source of his origin anyway? So that is the grandfather paradox, and the bootstrap paradox is kind of, it's in line with that. The bootstrap paradox is this causal paradox, causality. So what you have is that you have an object that exists and it should not exist. What caused it? So let's say you build a time machine. Okay, let's say it's possible to build a time machine. You go back in time, and let's say I have this object. Okay, see, this is an object that I have, and I go back in time to the time when I was 5 years old, and I give this object to myself, and that's how I acquired the object. So that would tell you that this object has no origin. Nobody made this object. So that kind of breaks down causality. Causality breaks down. So that is one of the problems with time travel. So the bootstrap paradox is essentially called a causal loop paradox. And what I'm talking about is a causal loop. Let's say I want to write a book, or let's say I've written a book, and I go back in time and give it to my younger self, who studies this book and writes the book. So then what's the origin of the book? That sort of thing. Okay, so it's what you see is there is a violation of causality. I mean, the universe is supposed to be causal. Every effect must have a cause. But in this scenario that we're discussing, the cause and effect loop happens in such a way that makes it unclear where the original cause originated. And then this brings us to philosophical questions about the nature of existence, the nature of creation. If an object can exist without an origin, if information cannot exist without an origin, it challenges the idea that everything must come from somewhere. It also raises question about time, about temporal logic, consistency of timelines. Can something exist if it was never created in the first place? And so on and so forth. So this is the bootstrap paradox. It is a causal loop paradox. It's a temporal paradox. Abhijit Banerjee says, is time travel possible using wormholes? Wormholes. So a wormhole is an Einstein-Rosen bridge. Okay, it's one of the solutions. It's a class of solutions of the Einstein field equations. So if wormholes, a wormhole is like a shortcut between two locations in space-time, not just in space, but in space-time itself. Okay, and if wormholes do exist, they could potentially allow for time travel. And how would this happen? So a world. Okay, let's go to Google and and try to visualize a wormhole. 1 second, let's put this on the screen. Wormhole. So a wormhole is this sort of it's a shortcut, as you can see here, between two locations in space-time. And if one of these, if one, you can see this wormhole over here on the screen, if one end of the wormhole could be moved at a very high speed relative to the other end of the wormhole, or alternatively, if one end of the wormhole could be placed in a strong gravitational field, then you would experience time dilation at that end of the wormhole, which is predicted by special as well as general relativity. Okay, so you'll have time dilation where time moves slower for an object or a person who is at that end of the wormhole. So in that mouth of the wormhole, you will experience time dilation, which would mean that the two wormholes are at different points in time. And this setup creates what's called closed time-like curves. These are paths in space-time that loop back upon themselves, and this theoretically would allow you to travel back to the past. So an object that emerges, that enters the wormhole at one end, could potentially emerge at a time before it entered. Okay. So yeah, so that's the deal. Now the question is, can wormholes actually exist? Are wormholes traversable? I mean, for a wormhole to be traversable, it would need some exotic matter within it. Otherwise, the wormholes want to snap shut. That's what the throats of wormholes want to snap shut. That's what the equations tell us. So you would need some exotic matter in the wormhole to keep the throat open, something like matter with negative energy density or negative mass, which is exotic matter which we've never seen ever. But yeah, you would need that, or you would need a cosmic string in there that simply can't break, and that could keep the wormhole open for it to be traversable. But could you still survive that, and so on and so forth? So yeah, theoretically possible, but is it practically possible? We don't know. But theoretically, yeah, one can actually conceive of thought experiments and scenarios in which one could actually do this. Harshal Sharma says, is intelligence merely a product of chemical reactions, or is it present at the beginning of everything? Intelligence, okay. There are lots of there are many scientists who like to claim that intelligence is just a product of chemical reactions. Emotions are the product of chemical reactions. The question I would like to ask is, what's the empirical evidence for this? What's the empirical evidence that a specific emotion is the consequence of a specific set of chemical reactions that happen in a specific location in the brain at a specific point in time? How do we know this? We don't know this. When you make a claim, you need to have evidence that backs up your claim. So these claims are just made flippantly and generally without any empirical, observable, reproducible evidence to back up this claim. So I'll tell you, just because somebody is a scientist doesn't mean that person is intelligent. Okay, I'll tell you that. There are lots of scientists who aren't the most intelligent people. So I don't agree that intelligence is necessarily a mere product of chemical reactions, or emotions are merely. It's possible. It is possible. But we don't have evidence for it. When we're talking about something like intelligence, when we're talking about emotions, we're talking about consciousness, and we don't know what consciousness is. We don't know the mechanism through which consciousness emerges, how it exists, where does it come from. We don't know that. Yeah, it looks like it's consciousness is it is located up here in the brain region. That's where we see the world from, but we don't really understand how the brain works at all, and we know next to nothing about consciousness. So I say we don't know. That's my answer, is we don't know. Okay, so we are almost at the end of today's thing. I have many more questions, but I have already crossed 2 hours, so I won't be able to take those. Should I take one more question? Okay, one more question. Amit Joshi says, if the particles from the standard model like quarks, electrons, neutrinos, etc. are elementary, then why do they split up in other particles in nuclear reactions like beta decay, where an up quark splits into a down quark, positron and neutrino, and the other way around for down quark with electron and anti-neutrino. Look, first of all, what are elementary particles? The particles in the standard model, like quarks, electrons, neutrinos, and so on and so forth, are considered to be elementary particles in the sense that they are not made up of smaller particles, smaller constituent particles. So these are the basic building blocks of matter, and of the fundamental interactions. Now, the process that you're describing in nuclear reactions, like beta decay, etc., it does not involve these particles splitting into others. It involves these particles transforming through fundamental interactions. So beta decay is a type of nuclear reaction where a neutron transforms into a proton. That's beta minus decay. Or a proton transforms into a neutron, which is a beta plus decay. These are transformations of particles. These are not splitting of particles. And behind this, at the bottom of this, is the weak nuclear force. So the weak nuclear force is behind the beta decay, beta plus decay, beta minus decay. In beta minus decay, a neutron, which is composed of an up quark and two down quarks, it transforms into a proton, which is two up quarks and one down quark. And this transformation happens because of the weak interaction. And one of the down quarks transforms into an up quark through the weak nuclear force. There's the emission of a W minus boson, and which will decay into an electron and an electron and a neutrino, and so on and so forth. So this is how it happens. So it is not an elementary particle splitting into another one. It is transformations of elementary particles and emissions of bosons and electrons and neutrinos through the process of the weak nuclear force. And there is a weak force, and there are quark flavors, and there is so much more in this. There's the emission of W bosons, W plus, W minus, and so on. So my point is, there is no splitting. Quarks do not split into other particles. They transform into different kinds of quarks through the weak interaction. And this is accompanied by the emission of W bosons that then decay into leptons, electrons or positrons, and neutrinos. So that is what happens, and that is the process. No splitting, transformations, and transformations mediated by the weak force as described by the standard model of particle physics. All right? Okay. That should be the last question. Let me take a couple of questions from the live chat in case you have any questions. Let's take a couple of questions from the live chat. Geopolitical Dubai says, why is desalination of ocean water so expensive, and how does it work? Desalination of ocean water. See, the ocean water is mostly water plus salt, various kinds of salt. The major salt is sodium chloride, which is your common table salt. So what you want to do is you want to desalinate this water. So how do you do it? One of the simplest ways is to boil it so that it evaporates. Then this evaporated steam, water vapor, you trap it, you cool it down and condense it into pure water without any salt. And what's left behind is the brine, which eventually becomes just dry salt and whatever else particulate matter. So it takes a tremendous amount of energy, heat energy, let's say, to desalinate just 1 liter of water, ocean water. You boil it, you condense it. The condensate is pure water, and what's left behind is what you don't want, the salt and whatever else. So you need to burn something. You need a heat source, fuel. That fuel could be coal, it could be petroleum gas, it could be solar or whatever. But the point is, it takes a lot of energy to do that, and that's why it is expensive. That's how it works, and that's why desalination is expensive. Ritvik Raj, multiverse existence. Multiverse, there are two major ways of arriving at a multiverse. One is the string theory multiverse, like I explained some time ago, 10 raised to 500 possible different kinds of universes, each with different physical laws. We don't know which one is ours. So that's the string theory landscape, or the string theory multiverse. And the other multiverse is what emerges out of the many worlds interpretation of quantum mechanics. And that's all about the splitting up of timelines based on various factors. I'll not go into the details. I have videos on this channel in which I've explained it in much more detail. So two different categories of multiverse: the string theory multiverse, the string theory landscape, and the multiverse that emerges out of the many worlds interpretation of quantum mechanics. All right, let's take one more question. Giuseppe De Fraia says, can technology and robotics solve the total fertility rate issue? Yeah, the global total fertility rates are plummeting, dropping everywhere, including in India. I ask because many women don't want to have children and are more interested in career education, all right, pursuits, rather than having children. Okay, so how can technology and robotics solve the TFR problem? I'm just trying to figure it out. Do we create artificial incubators in which you incubate embryos who are carried to full term, like in that movie The Matrix? Like that? I mean, it could be possible, but I'm sure there are lots of technological challenges in making this possible. I mean, this artificial womb environment needs to be very human-like. I mean, it should be able to sustain the growing embryo, the fetus, and provide it with all the nutrition and everything it needs. And obviously, it's not as simple as just that. It's not a machine; it's a human being, and that human being needs to be in the body of its mother and experience the sensations that fetuses experience while they are within the womb. And if that is not there, then will it develop properly? So there are lots of questions that we don't have answers to right now. And this sort of experimentation is obviously clearly unethical. I mean, some people would do it with primates and monkeys. In my opinion, even that would be cruel and unethical. So I don't know. Can you just set up baby factories in this manner? Right now, I don't think it's even technologically feasible to do it. In the future, in some dystopian future, somebody may try this. But well, I think the best way to solve the TFR is to do it the good old fashioned way, I would say. Okay, I think I'm gonna end over here. Karan says, will you make any physics course in the future? If there is demand for it, I will make it. I mean, this is the field I enjoy the most. Ombekeriger says, if time slows down inside a black hole, will the object that fell into the black hole survive till the black hole disappears? Due to release of radiation, we don't know. Look, an object, if it falls inside a black hole, depending on the size of the black hole, will be stretched. It will undergo a process called spaghettification. So if a human being goes into a black hole and the black hole is small enough, the human being will be stretched into ribbons. If it's a gigantic black hole, there will be no spaghettification. So it's paradoxically weird that the smaller a black hole is, the more spaghettification happens when an object goes inside. So the object, depending on the size of the black hole, won't survive, and we don't know what happens inside. Once you cross the event horizon, what happens inside, we don't know. I mean, according to general relativity, there is a singularity at the center, which means infinite curvature, infinite mass and energy density, which would be the destruction of any object that falls inside all the way there. So from the various views of a black hole that we have, it looks like objects don't survive once they go inside. Okay, that is the last question for today. I will see you in the next live stream, which is tomorrow. Tomorrow is going to be a totally different set of topics: geopolitics, history, and current affairs. But thank you so much for participating in this. Thank you so much for asking all your questions. I really appreciate it. And I will see you in next week's science, astrophysics, etc. live stream. I'll do it every week. I really enjoy it. So thank you so much. And I'll see you in the next one, whichever one you attend. Thank you.